A customer clicks buy. The order goes into the database, and that part takes about 20 milliseconds. Then we send a confirmation email. Then we render an invoice. Then we tell analytics. And only when every one of those has finished does the customer get a response. Watch the clock while that happens. Nothing here is broken. Every one of those calls succeeds. Almost 4 seconds. The database write is the only part of that the customer is actually waiting for. Everything else is work we decided to do while they watch a spinner. Here is where this ends up. The same endpoint answering in single-digit milliseconds. 200 jobs turning into more than 1,000 charges. A worker killed in the middle of a job. And one customer charged twice for the same order. We are going to build the thing that causes all of that from an empty table and then fix it. Here is the handler. 4 awaits in a row. Each one is reasonable on its own. Reading it top to bottom, nothing looks wrong. The problem is not any single line. It is that all 4 of them happen inside the request. So the response time is the sum of everything we chose to do. So move the work out. The same handler with 3 lines changed. Write the order, then write down that there is work to do, then answer. The email still gets sent. The invoice still gets rendered. Neither of them happens while the customer is waiting. Same benchmark, same concurrency, same warm database. The median goes from about 3,900 milliseconds to single-digit milliseconds. Throughput goes from 2.5 requests a second to over 500. Be careful about what that number means. We did not make the work faster. We did not make it smaller. There are still 93 jobs sitting in a table waiting for somebody to do them. All we changed is who waits. The customer does not, and the server is free to accept the next request. A queue does not make work disappear. It decides who is holding it. So where do we write the work down? Start with the simplest thing that could possibly work. An array. Push on one side, shift off the other, and a timer that drains it. This is a real queue. It has a producer, a consumer, and a buffer between them, and it is about 8 lines. If you have ever pushed a job onto an array and processed it later, you have written this. 3 orders come in. The queue depth goes 1, 2, 3, then restart the process. That is not a crash scenario, that is a deploy. And the queue is a variable inside a process that no longer exists. 3 customers were told their order went through. Nobody sent them anything. There is no error because from the program's point of view, nothing failed. So the queue has to outlive the process. It needs to be somewhere that survives a restart, which means it needs to be on disk, which means we already have a thing for that. The queue is a table. That is the whole trick. An ID, a type, a payload, and a status. No queue library, no broker, no new piece of infrastructure. If you already run Postgres, you already run something that can hold a queue, and everything from here is about what a worker does with these rows. Now we need a worker. It has to find a job, take it, and do the work. Select the oldest pending row. Delete it so nobody else takes it. Then do the work. 2 lines, and it reads exactly like taking something off a queue. With 1 worker, it is perfect. With 2 workers and slow jobs, it is still perfect. 5 jobs in, 5 charges out. It passes. Here are 8 workers, 200 jobs, and the jobs are fast this time. 200 jobs went in. Look at how many charges came out. Over 1,000. More than 160 customers were charged more than once for the same order. Nothing is wrong with those 2 lines individually. The problem is the gap between them. Between the select and the delete, there is a moment where the row still says pending. Every other worker looking at the table in that moment sees the same job and takes it too. With slow jobs, the workers are spread out and the gap almost never lines up. With fast jobs, they are all in that gap at the same time. This is why it ships. It behaves correctly in the exact conditions you test it in, and it builds 5 times in the conditions you deploy it in. There is a second problem in those 2 lines, and it does not need any concurrency at all. 1 job. One worker. The worker takes the job and dies. Not a bug, just a deploy or an out-of-memory kill or a machine going away. Then count the rows. No job because we deleted it when we took it. No charge because we died before doing the work. No error anywhere. That job existed and now nothing in the system remembers it. So Dequeue cannot mean delete. The job is claimed, not removed. We open a transaction, select the row for update with skip locked and mark it running. For update takes a lock on that row. Skip locked says that any row somebody else has already locked should be passed over rather than waited for. 8 workers hitting this at the same instant walk down the table, and each one comes back with a different job. And because we change the status instead of deleting the row, the job is still there if this worker dies. Same 8 workers, same 200 jobs, 200 charges, 0 duplicates, 200 jobs marked done. This is not a clever trick somebody found. It is in the Postgres manual, and the manual is very clear about it. Skipping locked rows gives an inconsistent view of the data. That makes it unsuitable for general purpose work. But it can be used to avoid lock contention with multiple consumers accessing a queue-like table. The feature was built for exactly this, and the sentence that recommends it also tells you what it costs. One more piece. A claim is a lease, not ownership. If a worker takes a job and dies, that row sits in running forever and nothing will ever pick it up again. Anything claimed longer than the visibility timeout goes back to pending. That is the line that turns a crash into a retry. And that line is also where the next problem comes from. Watch the order of operations. The worker claims the job. It charges the customer. Then before it can mark the job done, it dies. The charge already happened. The database has the row, but the job still says running. So the Reaper does exactly what we told it to do and puts it back on the queue. Another worker picks it up and charges the customer again. One order, $49.99, charged twice, $99.96 on a customer's card, and every single component here behaved correctly. This is the part people mean when they say a queue delivers at least once. Not that the queue is sloppy, that there is a gap between doing the work and recording that you did the work, and a process can die in that gap. You can make the gap smaller. You cannot make it 0 because the work and the record are two different systems. So stop trying to make delivery happen exactly once and make the work safe to repeat. One charge per order enforced by a unique index. And the first thing that happens when we try to add it is that Postgres refuses because the duplicate rows are already in the table. This is what fixing this actually looks like. The constraint you want cannot be created until you clean up the damage the bug already did. Then one clause on the insert, on conflict, do nothing. The second attempt hits the unique index and quietly does nothing at all. Then run the identical failure. Same worker, same crash after the work, same Reaper, same redelivery. The job runs twice. The customer is charged once. So what did we actually build? A table, a claim with skip locked, a visibility timeout, a Reaper, and a consumer that can run twice without doing damage twice. That is a message queue. Not a toy version of one, that is the mechanism. And it cost us. The response got faster, but the total work went up, and there is now a table to monitor and a Reaper to run. The delivery guarantee is at least once, and the only reason the customer is charged once is that we made the consumer safe. The manual told us skip locked gives an inconsistent view of the data, and we accepted that on purpose. And every one of those costs is also there when you use a queue you did not write. Using a library does not remove them. It just means somebody else chose the defaults. There is one thing we did not handle, a job that fails every time it is tried. Our Reaper will put it back forever, and it will sit at the front of the queue, starving everything behind it. That is a dead letter queue, and it is the next thing to build.